In the middle of one of the hottest cities on Earth, Dubai is planning a skyscraper that has to behave like a living organism. It has to make its own electricity. It has to pull its own water out of the sea. It has to cool itself in 50-degree heat without relying on the city's power grid. If its systems fail, hundreds of people inside are trapped in a sealed glass tower with no elevators, no air conditioning, and no running water. In that climate, a blackout is not an inconvenience. It is a countdown. This building has a simple but brutal requirement. On an ordinary summer day, it has to produce every watt it consumes and every drop of water its residents use. There is no backup cable quietly feeding it from a distant power plant. There is no hidden pipe from the city water network. If the sun disappears behind dust, if the wind dies, or if a critical pump fails, the building loses the basic functions that let it behave like a modern tower. That is why engineers treat it less like architecture and more like a life support system wrapped in concrete and glass. They started with the question most developers hate asking. How do you make a skyscraper that uses as little energy as possible before you even think about adding solar panels or wind turbines? A normal high-rise in Dubai is a climate control machine with apartments attached. Air conditioning alone can swallow 70% of its electricity because the desert never really cools down. The concrete structure heats up all day and radiates that heat back out all night. If you copy that design and just cover the roof with solar panels, you lose before you start. The numbers will never add up. The only way forward is to break the sealed glass box model. Instead of treating the outside air as an enemy, the engineers tried to use it. They wrapped the tower in a double skin, 2 layers of glass separated by a vertical air gap. At the bottom of that gap, vents let hot desert air sneak in. As it warms, it rises naturally and escapes at the top of the facade. That rising column of air acts like a gigantic exhaust fan that never needs electricity. It pulls heat away from the inner glass and drags fresh air into the building through carefully placed inlets. The effect is simple. The air conditioning system does not have to fight the full power of the sun hitting the glass. It only has to deal with the leftovers. Inside the concrete core, the tower hides another old trick, updated with modern engineering. Before fresh air enters occupied spaces, it is sent through long underground ducts where the temperature is much lower than the surface. As the air travels through these tunnels, it gives up part of its heat to the surrounding soil. By the time it reaches offices and apartments, it is already cooler than the air outside and much easier to handle. The building uses gravity and pressure differences as much as possible, so fans work less and chillers do not have to push air through kilometers of ducts. Even with all of these passive tricks, the building still needs serious power. Elevators, desalination pumps, controls, lighting, cooling equipment, and thousands of individual devices all demand electricity. The engineers divided the solution into 3 layers. A rotating solar skin wrapped around the tower, a ring of conventional solar panels spread across the podium and nearby roofs, and a wind turbine integrated into the top of the structure like a mechanical crown. The rotating skin is the most visible piece. Imagine a frame the size of several tennis courts sliding around the outside of the tower like a belt. It is covered in semi-transparent solar cells that convert sunlight into electricity while casting moving shade over the glass behind it. A control system tracks the sun's position and rotates the frame slowly during the day. At sunrise, it shields the eastern side. By midday, it hovers above the most exposed surfaces. By sunset, it has swung around to the west. Every degree of motion does 2 jobs at once. It generates power, and it prevents the apartments behind it from turning into ovens. On the roof, a vertical axis wind turbine stands inside a structural ring. Unlike conventional 3-bladed turbines, this one spins no matter which way the wind blows. Dubai is not famous for steady hurricane winds, but it does have reliable breezes at height and occasional strong gusts. Over a year, the turbine can cover a significant portion of the building's base power demand. Emergency systems, control electronics, water circulation pumps, and other loads that run whether people are home or not. The design team sized it and placed it so that if everything else fails, the turbine can keep the tower alive in a minimal survival mode, powering ventilation and critical pumps, even when the sun drops behind dust or clouds. The 3rd layer of generation sits on the building's shoulders. Every horizontal surface that sees the sun is covered in fixed photovoltaic panels. The roof of the podium, the tops of mechanical floors, the parking structures. These panels do not move. They simply feed power into the building's internal grid all day. Energy that is not needed immediately flows into a battery farm tucked into secure, fire-separated rooms near the base of the tower. Those batteries are not there for comfort. They are there for survival. In a worst-case scenario, they provide enough power to run stairwell lighting, basic ventilation, control systems, and the desalination plant long enough for a controlled evacuation instead of a blind panic. Water is an even bigger problem than electricity. A typical luxury tower with hundreds of residents and office workers uses hundreds of thousands of liters of water every day. In most cities, that is just a line item on the utility bill. In Dubai, the water does not exist until someone turns seawater into fresh water by force. For a self-sufficient building, that conversion has to happen on site. The engineers devoted a chunk of the podium structure to a compact desalination plant. Seawater is pumped in from the coast through buried pipes. Before it enters the membranes that actually remove salt, it passes through several layers of protection. Coarse screens that catch trash and marine life, settling tanks that let sand drop out, and filters fine enough to stop grains you cannot see. Only then is the water pressurized by heavy pumps and forced through semi-permeable membranes that allow water molecules to pass while blocking salt and other dissolved solids. Every cubic meter of fresh water costs several kilowatt hours of electricity. That is why the desalination plant is tightly integrated with the tower's energy systems. When solar production peaks around midday, pumps ramp up and fill elevated storage tanks hidden inside the structure. When generation falls at night, the plant idles, and the building draws water from those tanks. If the power system takes a hit, the control system knows exactly how many hours of water remain at current consumption rates. It can trigger rationing, turn off decorative uses like fountains, and prioritize drinking and sanitation over everything else. The building squeezes every possible use out of each liter. Gray water from showers and sinks does not go straight to the sewer. It is collected, filtered, and reused for flushing toilets and irrigating plants. Black water is processed in a small treatment plant in the basement. After passing through biological reactors and disinfection, it becomes suitable for landscaping, or, in emergency conditions, for reprocessing through advanced treatment units. None of this is glamorous, but it slashes the load on the desalination plant and pushes the tower closer to true independence. Cooling remains the hardest system to close. Dubai's outside air can stay above 40 degrees even at night. Traditional air conditioning fights that with brute force, high-pressure refrigerant cycles, high-speed fans, and massive rooftop chillers. Burj Al Taqa's designers could not afford that level of waste. After cutting the heat load with shading, double skins, and underground pre-cooling, they turned to radiant systems. Instead of blasting cold air into rooms, they pumped chilled water through pipes embedded in the concrete slabs above occupants' heads. A person sitting in a room cooled this way does not feel a blast of air. They simply feel a space that is quietly comfortable. Their body radiates heat upward, the cool concrete absorbs it, and the system circulates that heat away. Because water can carry far more energy than air per unit volume, the pumps moving it use much less power than fans and compressors in a conventional system. The chilled water that feeds those pipes is itself cooled by heat exchangers connected to seawater or deep underground loops, further cutting electricity demand. All of that technology needs a body to live inside. The tower uses a hybrid structure. A heavily reinforced concrete core handles gravity loads and wind forces. Around that core, the floors are built as prefabricated modules, manufactured off-site. Each module includes finished walls, pre-installed plumbing, wired electrical panels, and integrated ducts. In the factory, workers assemble and test them under controlled conditions. On site, cranes lift them into place and bolt them to the core and to each other. This approach solves several problems at once. The site can operate with a surprisingly small crew in a harsh environment. Instead of thousands of laborers standing in the sun cutting rebar and mixing concrete, fewer than 100 specialists handle assembly. Each module arrives with its own share of the building's energy and water infrastructure, ready to plug into vertical risers. If one level is damaged in a fire, flood, or structural event, it can be isolated, removed, and replaced without tearing apart the whole building. The deeper you go into the design, the more it looks like a machine with redundancies instead of a static tower. Every major system can survive the loss of one component. The rotating solar belt can get stuck in place and still function as a giant fixed panel. The wind turbine can shut down for maintenance while the batteries carry critical loads. One desalination train can be taken offline, while the others continue running at reduced output. The power management system constantly watches weather forecasts, occupancy levels, and battery charge to decide when to store energy and when to spend it. But independence comes with ugly edge cases. Engineers ran worst-case simulations, a sandstorm that blocks the sun for days and chokes the air filters, a heat wave that pushes temperatures above normal for a week, a grid outage that prevents any help from arriving. In one scenario, the building loses both a major solar array and its wind turbine at the same time. The control system responds by shutting down non-essential services, facade lighting, decorative fountains, high-power equipment in public areas. Elevators switch into an emergency mode that only serves a subset of floors. Cooling set points rise several degrees. Residents feel the difference, but the system buys time. There is a sharp line the building can never cross. If water storage drops too low, local regulations force evacuation. Modern cities do not allow high-rises to operate without guaranteed fire suppression and sanitation. The tower monitors that line constantly. If a large leak breaks out in a tank or pipe, sensors detect the sudden flow. Valves slam shut, alarms trigger, and the system automatically calculates whether it can keep running while crews repair the damage. If not, it begins an orderly shutdown, moving elevators to safe positions and directing people to leave before conditions become dangerous. This is what makes the project more than a marketing exercise. In a normal skyscraper, failure means a painful but manageable disruption. In a self-sufficient tower in a desert, failure can escalate quickly into a life safety problem. That pressure forces the design to be honest. You cannot fake energy balance. You cannot hide water that does not exist. Every engineering choice shows up in the numbers. Kilowatt hours per day, liters per person, degrees of temperature rise per hour if cooling stops. For Dubai, the building is also a test case. The city's population has exploded faster than its infrastructure. Every new district demands more power plants, more desalination capacity, more transmission lines. A cluster of towers that can manage their own needs reduces that load. It also offers a blueprint for remote projects far from any grid, research stations, resort islands, and industrial facilities in harsh environments. If the self-sufficient skyscraper works here, it can work in places even more isolated. The tower will not look as dramatic on the skyline as the tallest icons of Dubai. It does not chase height records. Its real competition is invisible. It is measured against the silent pipes, cables, and plants that feed every other building in the city. Those systems are hidden underground and behind fences. This tower drags them inside its own walls and forces them to operate in a confined footprint under unforgiving conditions. When people step into the lobby years from now, they will not think about any of this. They will judge it the way they judge every other building. Is it cool? Is it quiet? Do the elevators arrive quickly? Does the shower have enough pressure? The success of the project will be measured by how boring the experience feels on a daily basis. No drama, no outages, no strange restrictions. Just a building that quietly refuses to notice that it stands in one of the most hostile urban climates on the planet. Behind that apparent normality, every system will be doing something cities normally do for you. Making water out of seawater, turning direct desert sun and hot winds into power, storing energy and rationing it minute by minute, watching tank levels and temperatures like a nervous heartbeat monitor. In a world where more and more people live in extreme climates and strained cities, that kind of building is not just impressive engineering. It is a glimpse of how ordinary life might have to work when the grid can no longer guarantee that someone else will handle the basics for you.